Welcome back to the deep dive. If you're here, you're definitely looking for that fast track to being well informed. And today, yeah, we're executing something of a surgical strike on a, let's see, very specific piece of industrial engineering, our mission, to really analyze the sources we've gathered on the Tylok Pressure Gauge. We're not just, listing specifications. We want to dissect how the engineers managed to achieve this critical balance, extreme precision married to, well, radically simplified installation. If you appreciate the elegance of a small component solving, massive industrial headaches, then stick with us.
Yeah, this is a fantastic topic for a deep dive because it really shines a light on industrial reliability. The core theme today isn't just the gauge itself, its face value. It's more about how these meticulous, almost obsessive design choices, things like opting for a specific connection or an internal welding standard, how those translate directly into tangible operational savings and a huge boost in user confidence.
And what really hooked us, right out of the gate, was this promise that the gauge, housed in this pretty robust 2.5 stainless steel case. Yeah. It doesn't just report pressure accurately. It actively eliminates traditional installation failure points. It's like an engineer's shortcut to reliability. Okay, let's unpack this. Let's start with maybe the most revolutionary change here, and that's the way this thing actually connects to your system. The sources all highlight the tube stub connection. That's the primary installation innovation. For those of us maybe more used to the standard approach, why is this specific change such a monumental shift?
It's monumental because it takes aim at and eliminates the two biggest historical culprits for gauge connection failure. Simple as that. First, it completely removes the need for NPT threads. National pipe taper thread, gone. Second, and maybe even more impactful in daily practice, it eliminates the need for PTFE tape, that white sealant tape.
Okay, let's pause there for a second because, we can't assume everyone listening knows exactly what that means in practice. NPT threads, they're basically friction threads, right? They need to deform slightly, and they need a sealant, like that tape, to actually lock and seal properly. And PTFE tape, well, it's everywhere, but why is getting rid of that combination such a big deal for someone installing these systems?
Well, think about the failure modes. Just think about how those two things can go wrong. NPT fittings, they inherently rely on tension, right? And external material like the tape to seal. If you over-tighten, you risk stressing the material, cracking the fitting. If you under-tighten, well, it leaks. It's a very fine line. And the PTFE tape itself, it's notorious. It has a tendency to shed, leaving these tiny shreds of plastic contaminant inside your fluid system. Now, for really sensitive applications, think about oxygen service or high-purity gas lines. That kind of contamination isn't just annoying. It can be catastrophic.
Oh, right. So the tube stub connection just completely sidesteps that entire messy process. It just avoids it.
Precisely. Exactly. Yeah. It allows for a clean, leak-free, metal-to-metal fitting. There's no reliance on external sealants, no tape, no dope. The sources really emphasize that the design ensures proper orientation, and you get a secure seal pretty much instantly. You basically skip all those fiddly, failure-prone steps and go straight to operational security.
I can definitely see the immediate time savings, especially on a large installation job. And yeah, the reliability gain seems obvious. But here's a question. If this tube stub connection is so clearly superior, why hasn't it completely, taken over the industry? Is there a cost implication we're missing, or is it just the sheer inertia of dealing with decades of legacy NPT infrastructure? What's the barrier?
That's a really good question. And historically, yes, NPT fittings have generally been cheaper to manufacture and, universally available. Everyone knows them. But the hidden cost of NPT, that's the high rate of rework, system failures, troubleshooting leaks. What Tylok seems to be providing here is more of an integrated system solution. The slightly higher initial cost of the gauge is arguably justified by the massive reduction in labor, maintenance, and crucially, that contamination risk we talked about. For specialized or critical applications, that slight initial difference in cost becomes pretty negligible compared to even one system failure caused by, say, tape shredding.
Makes sense. The sources also highlight a more practical benefit for the technician on the ground. They note the gauge's design allows for easy orientation, streamlines the whole installation.
And that detail, that ease of orientation, it translates directly to less fatigue for the tech and, importantly, fewer mistakes out in the field. The practical takeaway here is just sheer efficiency. Most of these gauges, the sources say, can be securely installed simply by hand. You minimize the reliance on heavy wrenches or, complicated torque specifications, which are often the main culprits behind improper fittings, over-tightening. It's a beautifully simple, really elegant solution to what's been a chronic industrial problem.
Okay, that sets us up perfectly for the next piece of this puzzle. We've sorted out, or rather they've sorted out, the external connection errors. But now we need to make sure the instrument itself, the gauge, can actually handle the internal stress. And here's where it gets really interesting. Let's shift our focus now to the core engineering integrity, the long-term durability. We need to talk about the all-welded design.
Right. And what's fascinating here, what the sources really emphasize, is how far they actually took that commitment to welding. This isn't just about, welding the case shut. The key detail is that this all-welded integrity extends all the way through, right to the Borden tube itself.
Okay, help us visualize that for a moment. The Borden tube. What exactly is that component, and why is welding that specific internal connection point, why is that the ultimate test of durability?
The Borden tube is essentially the heart of the pressure gauge. It's the core pressure sensing element inside. It's typically a flattened or maybe C-shaped curved metal tube. When pressure enters the gauge and fills this tube, it tries to straighten out or uncoil slightly. That tiny bit of movement, that physical change, is what mechanically drives the needle mechanism you see on the dial. Now, in many, let's say, traditional or lower-cost gauges, this Borden tube is mechanically joined to the gauge socket, the part where the pressure comes in. And that mechanical joint, it's a well-known potential point of failure. It often involves joining dissimilar materials. Maybe it requires brazing or even soft soldering. And it's highly susceptible to stresses like thermal expansion and contraction, constant pressure cycling, and especially vibration. So by using a continuous, all-welded design, literally welding it all the way through to that critical Borden tube, they effectively achieve zero mechanical connection leaks internally. It's one solid path.
Wow. So they're literally eliminating the potential for any material creep or fatigue failure, right, where two separate pieces used to be joined. It's just one piece reacting to pressure.
Exactly. That's the core idea. When you eliminate those mechanical fittings, you create a component that behaves essentially as a single homogeneous unit under pressure. This drastically improves its resistance to vibration. Vibration can shake mechanical joints loose over time, causing drift or failure. And it ensures much greater longevity, especially under harsh, high-cycle pressure conditions where those joints would normally fatigue. It's really the difference between, say, bolting two pieces of metal together versus forging them into a single integrated component.
That's a really impressive commitment to structural integrity, down to the core sensing element.
Yeah.
And to back that up, the sources confirm the quality assurance side of things. Each and every unit is 100% tested. That seems to go well beyond standard batch testing you might expect for this kind of product.
Oh, absolutely. That 100% testing, it's like the final stamp of confidence that validates the whole rigorous design philosophy. It guarantees that every single unit leaving their factory meets the stringent accuracy standards they promise. You're not relying on statistical averages. It's a massive differentiator because it minimizes, maybe even eliminates, the risk of receiving an intermittent or worse, a damaged unit right out of the box. DOA gauges are a huge headache, so this commitment, it really ensures dependable performance and accuracy that technicians can trust absolutely when they're making critical system measurements or adjustments. It builds confidence.
Right, that makes sense. Now, okay, we need to address the real world, the complexity of actual industrial applications. Versatility is always key. A great design doesn't mean much if it can't adapt to the specific environment it's thrown into. So what range of applications is this gauge actually built to handle, according to the sources?
Yeah, the sources confirm this unit is really designed for broad application. They offer a very wide range of pressure options, going right up to quite high PSI ratings to fit diverse system needs. But perhaps more importantly for adaptability, they offer crucial customization in the case fills.
Case fills, okay, that's the liquid you sometimes see filling the entire gauge face, right? Mm-hmm. Behind the glass. Why are those different fill options so essential for professionals working in different kinds of environments?
They are absolutely critical for managing external factors, primarily vibration and pulsation. The most common fill you'll see is glycerin. Glycerin fill cases are pretty much essential in environments with heavy machinery vibration or where the pressure itself is pulsating rapidly. Without the damping effect of that glycerin, the gauge needle would just oscillate wildly, bounce all over the place, making accurate readings basically impossible. The liquid effectively cushions the delicate internal mechanism. But, you can't use glycerin everywhere. In extreme high-temperature environments, for example, standard glycerin might degrade, change viscosity, or even affect the gauge's accuracy over time. That's why having a dry case option is necessary for those high temp situations. And the sources also note the flexibility to have liquid fillable cases. This gives professionals the unique ability to choose the optimal fill fluid themselves, maybe a silicone-based fluid for wider temperature ranges, or even fill it on site if they have very specialized fluid requirements or encounter extreme temperature variances that need a specific damping fluid.
That level of flexibility really speaks to the needs of, well, someone like our learner persona who might be dealing with anything from a standard factory floor to a boiling hot process line or even a cryogenic facility. And for those really niche requirements, the sources do note the option for custom configurations, going beyond just the standard pressure ranges and case fill options.
Absolutely. The foundational promise, as we've discussed, is that every standard unit is manufactured to the company's pretty uncompromising engineering standards. That's the baseline. However, they clearly recognize that the industrial world is just full of specialized, unique challenges, things nobody thought of as standard. So they make custom configurations available upon request. That means if you have, say, an unusual process media that requires specific wetted materials, or a non-standard connection type, or a very specific pressure range or dial configuration, the same core reliability principles that all welded board and tube system, the simplified tube stub connection, can potentially be adapted to meet your precise, unique need.
Okay, so what does this all mean? Let's try to synthesize everything we've unpacked here about the Tylok pressure gauge. I think the core takeaway for you, the listener, is that this gauge is really defined by the marriage of two critical elements. First, you've got this extreme precision engineering, which is driven internally by that structurally superior all-welded design, right down to the board and tube. And it's backed by the guarantee of 100% testing on every unit. And second, you have this dramatically simplified and crucially leak-reducing installation process. That's achieved through the innovative tube stub connection, which cleverly removes those traditional problem points, threads, and tape right out of the equation.
Yeah, and if we connect this to the bigger picture, this gauge serves as an excellent sort of case study in industrial design philosophy. It shows that achieving excellence in professional tools doesn't always mean adding more features, more complexity. Often it means intelligently simplifying complexity, while simultaneously, and this is key, absolutely refusing to compromise on fundamental structural integrity and reliability. They essentially solve the technician's major pain points, those installation errors, the leaks, the contamination risk, without introducing new internal compromises like weak mechanical joints. That fusion, that blend of field usability and core durability, that's really what defines a truly dependable professional-grade tool.
That principle really does hold true across so many technical fields, doesn't it? Engineering, software, medicine. And so, here's one final provocative thought for you to consider as we wrap up. If eliminating something as seemingly simple as ubiquitous as PTFE tape and traditional NPT threads can provide such a quantifiable, significant leap forward in system reliability and ease of installation, where else in your professional life or even your daily routine are you currently relying on outdated multi-step, potentially leak-prone connections or processes, things you just accept as the way it's done? Maybe challenge yourself this week to look for similar simplification breakthroughs, those elegant solutions that manage to remove steps, remove failure points, while simultaneously increasing overall quality and reliability. See if you can spot them in the technology you rely on every day.